So I hope my screen is visible and I'm loud and clear.
Yes, sir. Yes, sir. It is visible, and I request all of the attendees to keep their mic on mute, except Ratnakar sir. And if you have any questions, post it in the chat box. We will take up those questions at the end of this session. Okay, great. Thank you. Over
Thank
to
you.
you, sir.
Thank you. Thank you, Ankur. So today we are going to talk on the topic of uh, applications of geosynthetics in railway infrastructure. So in this presentation, first I will brief about just the organization I'm working, followed by the topic. So to start with, I am basically working at McAfee. McAfee founded in 1879. It's a company having presence all across the globe in all five continents, and we are basically 140 years young company. Uh, we are basically providing the solutions to civil engineering, where we have developed our solutions through R&D, as well as the experience over the number of years. We have our own in-house softwares which can be used for various basically solutions. We are having 3,000 plus employees and 23 factories, which are basically being operated or looked after the markets around 70 plus subsidiaries. To start with, let's understand what is geosynthetics. So, geosynthetics are basically the planar products which are manufactured from polymeric material. And when they are used with soil, rock, earth, or any other geotechnical related material, which is a part of civil engineering project, that's called as the geosynthetics. So, prima facie synthetic products. However, there are other materials also which are being used in combination of soil, earth. So that's our natural materials, typically jute or coir, or sometimes steel or fiberglass are also being used. Now the various applications basically in railway sector, we can basically think of the different problems being faced, and accordingly the solutions are being provided. So these are like bezel reinforcement, uh, retention, so typically retaining walls, drainage of structures, erosion control, rockfall protections, hydraulic works, safety or noise barriers, tunneling, soil stabilization, and fencing and wire. So if we have to understand these different basically applications, we can look at, let's say, a cross section. Let's say we are talking of a cross section of a railway line passing through a hilly terrain, and let's look from the top, that is the hillside. So probably you may have a falling rocks where you may go for a rock fall protection works. You may have a lot of cut slopes where there are possibilities of the soil erosion, so where the erosion control solutions are being provided. Of course, when the steep cuts are there, they are combined with the nails or anchors with the flexible facings. You may use the bunds, basically the earthen bunds, which can be reinforced with geosynthetics. This can be used for noise barrier as well as even rockfall embankment itself. As far as the railway track structure is concerned, we can talk of track bed stabilization, where we are talking of blanket or let's say sub ballast or ballast stabilization. On the valley side, when we need to retain the soil, we are talking of soil retention, and then drainage. Of course, drainage, we are talking of a subsurface drainage, which need to be taken care for any geotechnical structures. And of course, the hydraulic works, typically wherever the water courses are intervening with the railway structure. So let's look at the first application, that is erosion control. So this photograph, what you see is from a railway project, but I will just take you through this. What is this erosion control we mean? With our solutions, we also take care of erosion control. This application is not less important than others due to the high maintenance cost in case of soil loss from slopes and the possibility to create instability in the embankment in the worst cases. To solve the common problems like embankment slope failure, water seepage into embankment, superficial erosion due to weather elements, the solution is the installation of reinforced geomat capable to avoid washout of washout and topsoil erosion. Also, that application could be designed from the technical point of view. We need to protect the slope from superficial erosion due to impact of the rain and wind. We know that it is not, we know that is not enough to completely cover the slope to guarantee the long-term performance. You need also to think about the surface stabilization and the saturate soil stability. For this reason, we propose our MACMAT with reinforcement inside, typically the double twisted wire mesh or geogrid. From the environmental point of view, is important to guarantee the natural revegetation process facilitated by the sun rays that pass through the geomat. We take care of it with an outstanding light penetration of the geomats. In our research and development process, taking care of several tests and installation done over years, we reach to the conclusion that best erosion control product must take into some key parameters. So these parameters are light penetration. So thickness of the geomats, the color of the geomats, water absorption, weight of the mat, roughness and runoff, and the uniformity. It is the balance between these indicators that generates the best solution. Geomat, typically let's say MACMAT, are made of synthetic materials, filaments entangled together to form a highly deformable layer of 10 to 20 millimeter thick, featured by a very high porosity. Typically, porosity is greater than 90% on average. Obviously, the porosity is required from the point of view of sunlight, what we discussed in previous slide. So for growth of vegetation, you need to have sufficient sunlight passing through these mats and which is received by the seeds which are on the slopes. They can be used on slopes along the banks of canal or river courses as well to convey liquids or drainage in association with geotextiles or geomembranes. So you can see that typically in erosion control, it can be on the, let's say, the cut slope side or even the embankment itself. These are basically sustainable and green solutions. If you compare the carbon footprint, typically, for these solutions compared to the other solutions was typically conventionally being could be adopted like of riprap or concrete, there could be a lower carbon footprint. And of course, they are economical when we are comparing with a long term or life cycle cost. They are easy to construct. It comes in the roll form. You unroll from the top of the embankment and then pin it at regular intervals. Obviously, once you have good vegetation, you see a good aesthetics. So you can see here a project from the southern part of India where a MACMAT is being installed with nails on a slope. The location is Hubli. So here the synthetic mat is being installed and these are the nails that's being put. This is a project from northern part of India. That's Alam Nagar, which is near Lucknow. So this is a railway embankment. So first dressing of the embankment properly and then watering it. After that, placement of a mat and then the seeds of the grass. After you do, let's say 1 or 2 months watering, you get a nice green grass. The photograph here you see is a cut slope. This is a project from southern part of India, where the cut slope is typically around in this project is around 70 to 80 degrees with horizontal, which is stabilized with the soil nails. And as a facing, typical there are number of facings available like concrete cladding or let's say shotcrete, but we recommend to use the high strength synthetic mats. The performance of this high strength synthetic mats is greater in terms of the vegetation growth as well as the deformations which will occur between the nails. So our experience typically in this application, this is one of the project in Russia. This is the Amur gas processing plant near the city of Sogondi, Amur region. This will be Russia's largest and world's second biggest natural gas processing facility. So MACMAT R which is steel reinforced geomat, was used to protect 26-meter railway embankment from the UST Para station of the Trans-Siberian Railway to the Amur gas processing plant to the construction site. In that case, the solution was designed also to save the slope from frosting and defrosting cycle in the uncovered soil. In this project, you can see the amount of MACMAT that being used is huge, and it's a very good example of adoption of synthetic mats for railway embankments. This is another project in which the reinforced MACMAT was being used. The reinforcement was in the form of double-twisted wire mesh, where this is being put on a cut slope. This is the project site in Philippines where the natural mats that's being used, that's the biomat being used. Now, after understanding the soil erosion, let's move forward to the other application, that is retaining walls and soil reinforcement. For every problem, the right solution, that's the requirement. So the reinforced soil slopes or walls are very flexible structures. In our portfolio, we deal with wraparound geogrid structures and our paramesh, terramesh with gabion facing and green terramesh structures combined with high-strength geogrids of Paralink and Paragrid up to the vertical walls of Macres. Vertical walls Macres are reinforced with high-strength geostrip. That's we call it as a Paraweb. The choice is related to the available space for the embankment, construction, and the availability of stones or filling material. Also, the environmental and weather condition has to be taken into account. Just to share a recent visit, that is yesterday itself. So I had visited the Indian Railways office, RDSO, and when we want to construct an railway embankment in a densely populated urban area, typically what you require is a very big footprint, of these embankments, and the land is very scarce and very expensive, and acquisition of land is a challenge. So there is exercise going on exploring the possibility of use of reinforced soil walls. So the common problem in the design of reinforced soil structures are basically embankment stability failure, the manage of differential settlements, and the interaction with the environment. Of course, the solutions are geosynthetics embankment in the form of slope reinforcement or vertical faced soil reinforcement. The geogrid provides resistance with an additional tension to the entire embankment. In fact, thanks to its high stiffness, especially when compared to the rigidity of the ground, it absorbs the tensile stresses without excessive deformation. This results in improvement in mechanical characteristics of the soil that guarantee the stability, that is global stability, local stability. Now, if we want to understand the cost comparison of, let's say, the reinforced soil structures, let's look at the cost comparison of TerraMesh system with conventional, let's say, crib walls or RCC cantilever walls. So this is a graph which is being borrowed from FHWA guideline, where you have the cost in dollars per square meter on y-axis and the height of wall in meters on x-axis. And you can see the most expensive solution is basically the reinforced concrete cantilever retaining walls, followed by the MSC wall, or let's say the reinforced soil wall with the metal, that is typically metal strips or the steel rebars, and then the crib walls and beam walls. Of course, you cannot construct crib and beam walls to very tall heights, typically lower heights. However, if you combine the cost comparison of the TerraMesh system, or let's say you're using a geosynthetics, this is what the lowest in all the options. So the challenges with the conventional solutions typically is high cost. They require more time to construct, because for constructing the reinforced concrete retaining wall, you need to provide sufficient time for curing of the concrete, and then only you can raise the height. Whereas in case of reinforced soil wall, you can build them at a faster speed because these are modular system off the shelf, very easy to install. Of course, rigid structures like the retaining walls cannot accommodate the differential settlements on poor ground. The differential settlement, let's say the criteria to permissible differential settlements in case of the RCC retaining walls is the lowest one compared to the reinforced soil walls, which are flexible, but yes, yet resilient. If we talk of the carbon emissions, of course, these reinforced concrete retaining walls have higher carbon emissions and they require the deeper foundation. So let's look at it from a graphical representation, what I just talked about, the additional land. So if we are talking of a railway infrastructure to be built, typically you may go for 1:2 slope. So you require, let's say, 2 times the height is what's the additional land. Or let's say from the edge of the track, typically, let's say the as per the formation width. Beyond that, you require this additional land. However, if you are able to construct a retaining wall, let's say with the reinforced soil structure, then you save this additional land. So you save the precious maybe agricultural land or urban land, which can be used for some other purpose, as well as you get away from the hurdles of land acquisition. Overall, these geosynthetics, when we use for soil retention, they are basically requiring less land. Of course, case to case, it may vary. Their economical could be in the range of 5 to 30% very easily compared to the RCC wall. Of course, these numbers will change these as per the site conditions, project locations, but this is overall a ballpark number. Typically, in the reinforced concrete retaining walls, you require a deeper foundation depth, whereas in the reinforced soil walls, you require typically shallow depth of foundation, typically 1 meter. Flexible fascia is one of the advantage of this system, which we are very resilient for earthquake response and of course have the lower carbon emissions. So the use of geosynthetics allow to solve some technical, environmental and economical problems. So as far as technical is concerned, that is basically smaller embankment print, shorter ballast height, higher basically factor of safety in terms of static and dynamic conditions. As far as environmental is concerned, you may use the in situ soil, so reuse of the in situ soil as a structural backfill is possible. Lower carbon emissions, low environmental impact, and of course, EPD, that is Environmental Product Declaration. There are the certifications are available for the geosynthetics materials. As far as economical is concerned, of course, they are cost effective, faster to install, and have low maintenance. So our wide range of products and extensive experience enable us to meet the client's need. We can offer a wide variety of face finishes, including the vegetation, rock, concrete, block, and paneling. If requested, we can basically enhance or alternatively prevent the vegetation growth. The use of our products maximizes the opportunity to reuse the site-owned or local material as a structural backfill, embracing the sustainability and reducing the polluting of the truck movements. The solutions accommodate differential settlements and seismic loads better than compared to the rigid structure. So these are some examples. This is a reinforced soil wall. We call it as a macress. It is concrete panel wall, which is built in United Kingdom. This is a reinforced soil wall which is built using the stone fascia, or both these walls are directly supporting the railway tracks. So we can offer very, let's say, versatile solutions which can be used to build the very tall reinforced soil structures. We have a paradrain, a unique new generation geogrid, which combine the reinforcement and drainage, which permits or let's say enables using the local soil. And of course, we have the software that's Maxstars, which is basically which can help the designers to design these structures using various standards available across the globe, like whether it is British standard or the French standard or the American standard. If accordingly, you can design using one software. So if we have to understand what could be the possibilities if we are building a railway structure, okay, let's say on the flat land, typically, or let's say requiring the retention on both sides. So you can go with a stone fascia or a concrete fascia, or you can go for a green fascia, or even you can use the simple gabion walls. The gabion walls may be made up with the mechanically even double twisted wire mesh. So the project photograph, what you see here is from the northern part of India, is a part of the project USBRL. USBRL stands for Udhampur Srinagar Baramulla Rail Link Project. This location is referred as the Bridge 40, where we have constructed a paramesh reinforced soil wall. Where this is the plan drawing of the project. On the left hand side, there is a tunnel through which the railway will pass. The tunnel length is approximately 6 kilometers. On the right side of the plan here is the railway station. The railway station, new railway station name is Riasi. And these magenta color lines, what you see here, these are basically the cascade or culvert, which is carrying the water coming from the tunnel through the backside of the embankment and taking it down. This green portion is basically top of the structure. That's the embankment. And then you can see there are different berms which are being built. Typically, height of maximum height of 50 meter was built in this project. So this is the cross section of the structure, where this is the bottom tier where we have used the stone fascia. The horizontal lines, what you see, these are the geogrids which are being designed to take care of the lateral earth pressure. At the back of the structure, what you see, magenta, then the red and the gray color. These are basically drainage arrangement. The magenta color line is a geocomposite drain, MAC drain, is a geosynthetic product. The red color is basically a chimney drain of thickness of approximately 0.6 meter, and followed by the gray color one is a chimney drain with higher thickness. So this structure is built in different berms. So each berm is approximately 10-meter high. At each berm, we provided a channel to take care of the surface flow. On the top here, this is the embankment, which is again reinforced with the geogrids. And this is the area where the railway tracks will be laid. So this is the project, and you can see the condition before starting the construction of the reinforced soil structure. This is the culvert or cascade which is carrying the water from the tunnel, taking from at the back of the structure and down here. This is the bowl shape area which was required to be filled. Now, as the tunneling operation took place, there was a lot of tunnel muck which was being derived during the tunneling operation, and this was stacked at one location. Disposal of that tunnel muck was also a challenge one. So in this project, the reinforced soil structure was designed to use local soil, that is the kind of a waste material, that's the tunnel muck itself, to build the embankment and solve the problem of storage of this material. Because from the environmental point of view, we cannot dump this tunnel muck in any area because it may contaminate the water sources. This is the photograph showing the level checking after excavation for achieving the bottom of the wall. So this is the exactly, you can say, founding level of the wall, followed by placement of the soil. This is basically tunnel muck, and then compacting with a vibro roller of 10-ton capacity. After preparation of the foundation, the first layer of reinforcement, soil reinforcement paralink was installed, and on top of that, the backfill was sprayed. So in this photograph, you can see the geogrids being placed at the wall location. And this is how the compaction of the backfill, or what you call a structural fill, is being done. The maximum thickness of the soil that's compacted is around 200 millimeters. The density requirement was 98% of the maximum dry density to be achieved. While compacting, the heavy roller of 10-ton capacity was kept around 2 meters away from the fascia. In this photograph, what you see is a green fascia, that is a green terramesh system. So you can see this is a green terramesh system which is formed with the welded wire and double twisted hexagonal wire mesh. The required inclination is being provided with the help of the stirrups. And the double twisted wire mesh acts as the fascia itself and the connection itself. And the connection of this system is through friction. So typically the double twisted mesh is around 3 meters long, which is interacting with the adjacent geogrid, providing the connection. So this is the photograph of the structure just after completion. total height of approximately 50 meters. On the right side, what you see is the development of vegetation during the construction process. So this is the completed structure. And on the right side, what you see here, this is basically the railway station. That's the Riasi railway station under construction. So this is the first wall with the geosynthetics for with railway loading in Indian Railways. In this project, there were around three structures, that is 40, 41, and 42. So the maximum height was for a structure bridge 42. The height is around 55 meters. In this project, all three structures, the tunnel muck was used for building the reinforced soil wall. Here, the green structure is being basically green fascia is being used, so it's a greener solution compared to conventional reinforced concrete wall. Uh, many places the this kind of technology is not being used, and basically we are consuming a lot of land in terms of building the railway embankments, and we can save this land, which will be useful from various other purposes like agriculture or urban use. Let me take you through the second project. This is the project which is built for DFCC. DFCC stands for Dedicated Freight Corridor. This was for the package 303, which is in the north part of India, above Delhi. It's a city near Meerut. So the project line is Khurja Pilkhani railway line. In this project, land acquisition, of course, was the pain area. And when we had proposed to use this reinforced soil wall, so the DFCC had said we can go ahead if we have a similar case references of reinforced soil wall being used for railway loading. So we could show them the project done in UK. That's we call it as a reading viaduct. This project was showcased, and after that, the project management consultant and the DFCC officials got the confidence, and then in one structure, this reinforced soil wall was built. In this reinforced soil wall system was use of a concrete fascia with Paraweb, which is a geostrip, is being used. So Paraweb geostrip is laid in a zigzag fashion, which is connected to the fascia through a connection. So the advantage of this system, of course, is a faster construction, of course, require less land, and there are cost savings. So this is another project which is being uh, completed. And another uniqueness of this project is the axle load. The dedicated freight corridor has an axle load of around 32.5 tons. So the structure was designed for that. In this project, the retaining walls, then you had the embankment followed by the railway track. Taking you through the another project that is from the Indonesia, moving away from India. Now it's in Indonesia. This project was built for connecting the airport from the city. And here we have used our paramesh system, that is TerraMesh and high strength geogrid paralleling. The maximum height of wall was around 14 meter. Uh, in this project, as the alignment was passing through urban area, there was no possibility of building the embankment, and vertical retaining structures was required. So the reinforced soil technology was proposed here. In case of this TerraMesh system, around 3 meter long DT mesh is used as a friction connection. Moving to the another project that's from Czech Republic. This is basically the reinforced soil structure with the green TerraMesh fascia. This is again for directly supporting the railway embankment. You can see the cross sections of the structure. So one which is showing as basically the embankment, and then after some distance, the reinforced soil structure is being built. So these are the photographs showing the construction of the reinforced soil structure using the green TerraMesh system. So here you can see this is the fascia of green pyramid system, and then the reinforcement in the form of geogrid that's being utilized. These are the photographs of the structure of completed structure. You can see here this is a slope which is built using the reinforced soil technology, and you can see here also the berms are being provided and then followed by a railway track on the top of the slope. This is, you can say, a bird's eye view of the completed structure on the both sides of the bridge, right? And you can see the embankment being constructed a steeper slope inclination than the conventional typically slope of 1:2, 1 vertical as to 2 horizontal. This project is completed in the year 2020. Moving from Czech Republic to the Denmark, this was for a metro line connecting the airport area with the central Copenhagen. As the location is urban area, so it was required to go for, let's say, a steeper or vertical structures where reinforced soil technology is being used. Here, the terrace system was being used, and the project is started around 2004 and finished in December 2005. This is the cross section of the embankment, reinforced soil wall embankment. These are the photographs during construction. So you can see the green mesh fascia that's being adopted, followed by a stone fascia at the top. This stone fascia is basically a noise barrier, or you can say noise plus safety barrier. An example of how the culverts also can be accommodated in the reinforced soil walls or slopes. Now moving from soil retention to the water management. So typically, whenever a railway line crosses the or being built or large area, so there are inevitable it will be crossing the various water courses. So it is important to provide the scar protection around the piers and abutments, or protection along the river banks or channeling works. Usually it's done using the mattresses and gabions. Now we have a product called Reno Mattress Plus with X ties. So where X tie is experimentally developed and patented to tie to the maximize the structural resistance of the mattress. And this mattress is made up of a steel wire with heavy galvanization, and on top of that, a polymeric coating polymac is being applied, and the polymac has very high basically protection against mechanical damage and chemical degradation. R&D was carried out in the year, let's say 2019-20, and before that around 20 years back, the R&D was carried out. So this research is being carried out at University of Colorado, where the flume testing is being done. And the outcome you can see is the shear stresses on the x-axis and the thickness of the revetment. So if we talk of the conventional riprap solution, usually you will see the thickness ranging starting from 0.4 meter to as high as 1 meter. If you use the conventional mattresses, it can start at 0.17, can go up to 0.5 meter. However, with the X-Tides introduction, the Reno Mattress Plus, the same mattresses which were reinforced or additionally with the X-Ties can offer a higher shear stress resistance compared to the both solution, that is with mattress and with riprap. So in the application with high values of shear stresses, Reno Mattress Plus is over 73% more efficient compared to the riprap. In terms of the carbon emissions, if we have to talk, you can see here, if we compare the riprap with the Reno Mattress Plus, we are looking at around 82% lower carbon footprint. And if we look at the standard mattresses, we are looking at around 28% carbon footprint saving. So some examples, this is protection of a culvert using Reno mattress at dedicated freight corridors TP303. This is a bridge abutment protection at SWR in the southern part of India and Komodavadi. So of course, with this reduction in thickness is possible, which leads to the economy and reduction in carbon footprint. So example of how these matrices can be used when we are having basically waterways crossing the railway alignment. Now, from moving from the water management to the soil stabilization and ground improvement. So another design challenge with the railways is the construction of the structure. The high dynamic load generates the infrastructure permanent damages. This causes basically uncentered or unbalanced load transmission, foundation soil not homogeneous or having very poor bearing capacity, additionally water infiltration, and inadequate foundation compaction. Now, the uh, main constraint of the this kind of structures is basically limited space, and basically ground morphology. So with the uh, application of this dynamic load, the how the load is distributed over area is important. If we are able to distribute the load over larger area, then of course the pressures going to the formations are lower. And finally, this helps in controlling the long-term deformation. So use of geogrid reinforcement allow increasing the spreading footprint on the foundation of the limited load applied. The interlocking of the ballast with the MagriDG, that is the extruded geogrids with a big aperture, guarantee the position of ballast in long term, and then you have very less maintenance. So to show the pictorial, let's look at the railway track bed where you have the ballast and then let's say the formation or the blanket layer. If it is existing formation, you may use the biaxial geogrid and geotextile here during the maintenance purpose. So typically biaxial polypropylene geogrid, that's we refer as a MagriDG, and a geotextile, typically non-geotextile. If it is a new construction, you can use the geogrids in the blanket layer and the geotextile as the separation and filtration. Here we have one of our design tools developed for railway ballast and subballast design. As you can see, the design inputs are typical. One of the train load, train speed, number of trains per day, number of cars per train. Based on our design experience in the design of railway application, we have developed a design tool for optimization of railway ballast and the subballast. The method used to design the geogrid stabilize railway ballast and subballast, which considers the wheel loads, the number of wheel passes, the geometry, railroad, characteristics of subgrade, and the properties of geogrid. The proposed design method is an extension of the methods available for design of stabilized road bases as is based on same engineering principle. The most recent research is on the behavior and basically properties of railway ballast have been considered and introduced in the design method. This design approach allow important savings in use of granular materials in railway projects. An example of railway basically track stabilization. This is from northern part of India, a project near Delhi. That's basically partly near Haryana, where 1 meter thick blanket is reduced to 0.4 meter, where you can see the construction sequence. First, the placement of a geotextile layer, which is acting as a separation and filtration, then placement of the half layer of the blanket or subballast, then placement of the MagriDG, that is biaxial extruded geogrid, finally laying of the remaining part of the blanket, and then placement of the ballast track. So in this project, we did a field testing to understand the EV2 modulus, that's basically modulus of elasticity at second step loading as per DIN 18134, which is recommended by RDSO in their guideline GE14. So in this, the testing sections were of 0.3 meter thick blanket and 0.6 meter thick conventional solution without geogrid. And when we conducted this testing, so you can see in the Google map, there are the two different locations where unstabilized and stabilized sections were being tested. What we observed that the modulus of the ballast blanket layer without geogrid or unstabilized section is around 192. If we reinforce it with geogrid, it is increased to 296 megapascal. So this shows the efficacy of the geogrid stabilized layer. This is another project from Bulgaria where this is a case history of ballast stabilization done according to this design method, what just we discussed. The construction of new line in railway line in Burgas in Bulgaria. We use a non-wound geotextile as a separation function and Magrid EGS for stabilization of the ballast. This allows important reduction of the ballast height and the reduction of the project cost and the time reduction. The design was requested to minimize the differential settlement even if the soil was not so stable. Now moving from the stabilization to the basal reinforcement. So in case of soft soils, typically the ground improvements is carried out using, let's say, piles. So you can basically get away of the pile caps with the help of the high strength geogrids, which will span between the piles, and you can basically change the spacing of pile and optimize the pile cap design. The paralink geogrids, which come as high as around 1600 kilonewton per meter, which are BVS certified. This is a project from the eastern part of India, that is Agartala Kura project. This is basically a railway line between the India and Bangladesh. Here the soil was very poor in terms of SPT standard penetration value. It's around less than 2, it's typically 1, and the challenge was limited construction time. So because of the very poor soil condition, it was designed to accelerate the settlements which may occur over a period of time. And the acceleration of settlements were done using the prefabricated vertical drain. A layer of high strength geogrid was placed on top of this prefabricated vertical drain. The purpose of this high strength geogrid was, when we construct the embankment, we can reduce the number of stages and avoid the slip failure. Another example of basal reinforcement application along the Italian high-speed rail, where this is the map which shows the network of the high-speed rail, and where the high-strength geogrids paralinks were used as a basal reinforcement in order to improve the stability of embankment and limit the differential settlements, often in combination of the prefabricated vertical drains. Obviously, basal reinforcement of embankment tracks based on cohesive soils in order to avoid any settlements, especially when the embankments were constructed to the rigid structures. So some photographs of the project sites from Italy for high-speed railway. This is a project photograph from Denmark project site, where the blocks of concrete, what you see are, these are nothing but the pile caps. And then on top of this, the soil was placed, and then the placement of a high-strength geogrid paralink. So this is the photographs from the same project where the geogrids were used for distributing the load between the piles on the pile caps. Now moving from the basal reinforcement to the drainage solution. A drainage system we consider is the drainage behind reinforced soil structures to avoid the failures of the structure. The drainage of the rainfalls from the ballast self-draining layer to avoid water intrusion into the embankment structure. The anti-capillary rise from the bottom of the base to the embankment. So with the climate change problems, every day is more important to evaluate the adequate design for the drainage too. The water is not collected in the right way could create problems to the stability of the structures. To be effective, a good drainage has to remove fast and the water from the railway tracks to protect the reinforced soil structures. It is well known that water is one of the main elements of risk for the integrity of the infrastructure. The railway one is no exception. In fact, the rise in the groundwater level or heavy rain leads to reduction in the resistance of the soil, with the consequent risk of collapse or subsidence. The master product for drainage as the geocomposite drains. Typically, they are easily substitute to the natural gravel. These are made with two non-wound geotextile that works as filter and separator, protect polypropylene mats draining for the mag drain W used to collect the water in horizontal drainage systems and for anti-capillary layers as an alternative to the natural gravel drainage layer. Here we also picture of a paradrain, a unique draining grid that could be used to build the embankments with marginal soils used as a filling material. The grid guarantees the stability of the structure, and the drainage channel helps to remove the water content from the soil that speeds up the consolidation of the layers. Now looking at the drainage behind the retaining wall. So this is the typically abutment or retaining wall behind that. As per the RDSO guideline, typically a 600 mm thick hand pack boulder is used. However, there are issues of the hand pack boulders in terms of the quality of the boulders, the packing of the boulders, the workmanship, the time required. Of course, sustainability point of view, we are consuming the natural metal. This can be easily replaced with the drainage composites. Also, you can use these drainage geocomposites, let's say in a cutting sections at the drains, the sedges, to keep the formations basically dry. So very smart solution for the drainage is the mag drain, trench drain, a geocomposite drain specifically engineered for vertical drainage. Fastest way to build a trench with very little excavation and ready to use with the drainage pipe. This is a case study from the Eastern Dedicated Freight Corridor from the northern part of India, where the mag drains were installed behind a box culvert. This was a demonstration where you can see a pipe being put at the bottom. And this culvert, approximately 30-meter long, around 2.5 meter height, is covered within 4 to 5 hours completely with drainage complete, whereas it could have taken a number of days to construct the hand packed boulders. Obviously, the speed is higher, the consistency is good. Even the drainage composites can be used as basically replacement for the, you can say, the anti-capillary layers, typically which are used or made with the sand layers. So this is a project basically from the uh, western part of India, where the geocomposite drains were used as anti-capillary layers. Similarly, in Italian high-speed rail, the drainage composites were used typically behind the retaining walls as well as below the embankments. In order to demonstrate the long-term behavior, we asked to the Italfer railway administration here in Italy this that certificate of excellence about the use of MACD in Italian railway network. Italfer, part of RFI group, has installed our drainage products for new high-speed tracks. Approximately 150,000 square meter of MACD installed. Installation started in 2000. The high-speed tracks are in service since 2007 without any problem related to the use of MACD. Now moving from drainage, some special solutions for special needs. So it's a McAfee's solution, ultimate wing breaking fencing. So prior fence effectively destroys and reduces the wind velocities. It can also use to control the drifting sand. From the cold climate to the hot climates, another special solution for railway special need. When you are in desert and the sandstorms create problems up to the train derailment, you need a wind breaking fence. It is McAfee's solution for the ultimate wind breaking fences. Parafence effectively destroys and reduces the wind velocities. It can also be used to control drifting the sand. It's lightweight, easy installation, durability. In fact, it is not the it's a rot proof and unaffected by sunlight. Rain, salt water makes an ideal choice for the type of the application. So not only performance certification, but also the environmental and digital ones. In all the presentations, we talk about how important to have a correct design for every solution. A design cannot be done without a certified numbers. As McAfee, we invest a lot in certification in order to guarantee the behavior and quality of our products. In particular, we want to talk about EPD certification that gives the information on environmental impacts of product life cycle, reducing energy material consumption. You can find all the information about that on our website, mcafee.com/pd. We are also update about the new design approaches. We really trust in the present and future that the reason since a couple of years we start to create our digital Gemini of our products in order to create a beam library of our solutions. Today, you can find, download, and use all the products on Beam Store. For further info, please visit mcafee.com/bear. So with this, I would like to really thank you for patiently listening and would like to receive the questions.
Thank you, sir. Thank you for such a detailed explanation. We really got an insight on how geosynthetics and geogrid use of this can affect the rail industry, and how it can, create new solution as compared to the conventional approach that are being used. So, thank you for that. Also, we got to know about the environmental impacts as well, and the cost impacts in the railway projects as well. So that was another insight that we got to see. I have also a couple of questions, but before I ask my questions, I would like to ask all the other attendees. Can you please share your question in the chat box or raise your hands? We can go to you one by one. I think Sri Nagesh sir has already raised his hand. Yes, sir. Please go ahead.
Yeah, Ratnakarji, thank you for the wonderful insight. As Ankur rightly said, we are in the PWI domain for so many years, but we never knew that there is so much of engineering below the railway track. So thank you very much for the insight. And my question is, are the solutions customized or is there a generic solution?
These solutions are basically, you can say, the customized one. Of course, each site is very unique and we need to design accordingly. So I would say it's customized one based on the site requirements.
And next is, as you know, that in Indian Railways, what happens, the embankments are not really built to the required standards, like you have to leave it for a couple of rains for the embankment to settle and all. And then what happens is it finally ends up in the track getting track lowering happens actually. So is there a
Yeah.
solution to this, take out a minimum of some portion of the topsoil and then replace it with some solution so that the impact of the track structure per se will not have that much of impact in spite of the not so good constructed embankment?
Right, sir. So ideally, the earthwork shall be done, as I said, maximum 200 mm compacted thickness to 98%. Then usually we don't encounter an issue. Basically, the tallest embankment what we have seen for railways track we have built is around 55 meter in near Katra, Riasi. So that structure has a ballastless track, first ballastless track of Indian Railway. And there were a lot of concerns. There could be settlements. Usually, what you rightly mentioned, typically, if not being properly compacted, there are possibilities of the settlement. So one is, of course, not to get into that area is compaction. But in case if you have tracks which have this kind of issues, uh, typically it depends on the what kind of soil is being used, whether ESQ1 type of soil, let's say, or very clay soil. What can be done is below the like old, if it is old formation, you don't have the two-layer system of blanket and ballast. It's typically just the ballast. But in that case, you will need to remove at least some portion of the soil. Typically could be 0.3 to 0.5 meter and compact it very well. And in case it is expansive soil, it's better to provide a layer of a drainage composite or a membrane so that to avoid the shrinkage and swelling of the soil, which is usually through the presence of water. If we are able to cut the water itself coming from top and then place this geosynthetic, then the rehabilitation could be done. There are a lot of rehabilitations done in Indian Railways using the extruded geogrids and geotextiles. Yes, in case you have foundation itself, the natural ground itself is a soft, that's a different uh, altogether problem. But if you have a very good foundation and just the embankment, then you can go with this geosynthetic. What it happens is the geosynthetics are going to distribute the load very wider area. So pressures going on the formations would be quite low, and that's why you would be able to maybe maintenance could be delayed. I don't think it will be avoided because of the poor construction done initially. So the maintenance cycle we can basically have a longer period.
Super. Yeah. Thank you. Thank you, Ratnakarji. I'll give opportunity to others. Thank you.
Yeah. Thank you, sir.
Any other questions? If you have some questions, you can paste in the chat box as well. I will take up the questions from there. So meanwhile, sir, I have a couple of questions. I think in one project you are talking about reducing the depth of blanket. I think it was a project in Haryana where you reduce the
Yes.
blanket depth from 1 meter to 0.4 meter after use of geogrid and geosynthetics. So
Yes.
in terms of percentage, how cost effective was it for the client? How much
Yeah.
reduction in
So
cost they achieved? Yeah.
yeah. So I would like to give you a reference of couple of cases. One, of course, is Gurgaon, Haryana, partly. Another we did in Madhya Pradesh, that was for an NTPC project in Gadarwara. So in both the cases, there were savings for the contractor. In the of course, I don't know the exact numbers of saving, but I know it's a 10 to 20% was the range. In Gadarwara project, one was the cost saving, but the another aspect was of the operational logistics difficulty. The siding was to be constructed, and for that the access was crossing the main railway line, that is a central railway line, you know. So the dumpers which are carrying the blanket material, as being a very busy line, they had to cross this gate, and there was a lot of time which was getting lapsed, and the contractor were requiring a lot of additional dumpers. But when the thickness is reduced, so the amount of material mobilized was reduced. So one is the cost saving, that is directly on the material itself. But apart from that, there are intangible costs related to the machinery, wear and tear, the time, which was very important for them.
Yeah.
We did
Okay.
one interesting instrumented case. I didn't show here. We did an instrumentation case in DFCC. So there also we measured the stresses using with and without geogrid. So there was again the cost saving, because one is the availability of blanket, another is the quality of blanket to be maintained is another challenge. You may be aware of that situation.
Yes. And one more question, sir. How difficult was it to get the approval from railways for that particular project? And because
Yeah.
I was in my previous company, I have actually faced this issue myself. It was a DFCC project, and it was very hard to get the approval. We did not get it in the end. So
Yeah.
yeah.
So you have hit the nail actually. So for example, the DFCC case, what I mentioned, the results were very encouraging in line. However, we struggle to get an approval, not because of any other reasons, but typically contract is binding on the contractor and the authority. So there were some difficulties in going beyond the contract. So that was one of the reasons. The other project where the siding were private, we could basically get it through the private owner itself. And the railways were mentioning that as this is a private, we don't worry about it. It's the lookout of the private owner. However, we worry about the connectivity with our main line. So they were fine. So approval of such technologies in Indian Railways is a challenge, is because of the exposure of engineers to this technology, number one, and typically the contracts which are getting formulated at the time of the tender itself. Uh, Sometimes it's difficult to deviate because of our overall processes of the contracting.
Okay. Okay. Understood, sir. Thank you. Thank you, sir. Any more questions from anyone else? We still have some time. We
Ye-
can take those queries.
Yes, sir. I have one question. So when it comes to the USBRL station, so when I speak about the slope, when the geosynthesis added, is there any variation in the slope values, sir, for the benching or the berm
Uh, Variation in the slope
slope for the
value.
banking angle? Yeah,
Oh, angle. Okay.
yeah.
Hello. I think is there some kind of a technical glitch? We're not able to
Yeah,
see. Let me just message him separately. I'll ask him to rejoin.
yeah, sure.
Sorry, my network had a issue.
Oh, yes, sir. Oh, you're audible now, sir. You can go ahead. Hello. Are we audible, sir? Just give me 1 second.
Hello.
Yes, sir. Yes, sir. You're audible now. Yes, sir.
Yeah. So yeah. So in the USBL project, we went for a steep slope of around close to, if I'm not wrong, around 65 degrees.
Okay. Okay, sir.
We have another question from Prince Joshi. He has posted it in the chat box. So, how useful are these technology when it comes to its use in port connectivity, rail links, marine clay regions?
Yeah. So very good questions. Yes. Typically, when you have marine clays, as I showed, a case study of Agartala where we had very soft soil. So, combination of prefabricated vertical drains or sand drains or columns, along with the geosynthetics, can be useful for improving the ground improvement itself. So this technology is very much useful basically for port connectivity, where we are going to encounter this soft soils, and uh, this technology is one of the most cost effective compared to other conventional solutions.
Uh, yeah, Sri Nagesh sir. Yeah, please go ahead.
Yeah, Ratnakar, in extension to that question, I saw a project when I was doing a project in Malaysia. There was a viaduct for around 20 kilometers long, which is on a marshy area. Okay, so they just built a viaduct and they connected the tracks. So is this solution really economical when compared to a viaduct construction for say 20 kilometers?
Yeah, very much, sir. Actually, viaduct would be very expensive. You can just calculate the cost of earthwork for an embankment, which is
Yeah.
nothing compared to the viaduct cost, and the ground improvement. What we are talking with the help of prefabricated vertical drains or sand drains is not so expensive. So yes, it's definitely very economical solution. Just to give you an idea, there is a project in Bihar. It's called Ganga Path. Okay, it's
Yeah.
along the banks of River Ganga. So some portion of that Ganga Path is on the embankment, some portion on the viaduct. So the portion of the embankment is quite cheaper compared to the viaduct cost.
Okay. Okay.
Even overall, the reinforced soil wall system, if you just compare, one is normal embankment, even the reinforced soil wall, what we talk, is going to be much more economical compared to the viaduct. So if you see the roads, typically in the roads, you have a bridges and the approaches are built with these solid retaining walls. The
Oh.
reasons for that is there is a lot of cost saving.
Thank you.
Thank you, sir.
Thank you, sir, for addressing our queries. Is there any other question? So I'll take that as a no. So thank you, sir. I think there are no other questions or queries from anyone else. Thank you for sir giving us your precious time for this session and agreeing to be a part of our ongoing effort to conduct these monthly trainings and monthly sessions. This also helps in knowledge gain, as well as it helps the PWI members to complete their CPD hours as part of their continuous professional development as well. So thank you very much, sir, for being a part of this session, and hope to see you again soon in some other session. We'll call you back once again if you are free, and if you have some time, we can again connect. Thank you, sir.
Sure. Thank you, PWI, for this opportunity. Thank you all.
Thank you all.
Thank you. Thank you, everybody. Have a good day.
Thank you.
Thank you, everyone. Bye bye.